Hello, hello.
Hello. Thank you.
Do people stay? Oh, after? Much later. That's rough. Hopefully the whiskey got drank.
Yeah, didn't see my message.
Oh, no. I didn't look at Twitter yet. Oh, gosh. Oh, no.
For the questions, we'll go first. Yeah.
Beauty.
Is it true?
No. It's just- So I'll monitor too. I have the online questions come in. So Oh. 1 second. I was. Oh, I closed it. All right, 1 sec. Okay, I can't close my laptop.
There will be
We found that there are some reasons. I'd rather miss them more than what.
If someone lost their passport, we have one at the registration desk. If Nam is in the room, your passport is at the registration desk. Nam Hun Ko.
Good. Thank you, everyone. I think we'll start the final session here of Ches. So thank you for sticking around. This will be an exciting session on RISC V. So there's 3 talks. They're all in person. So to keep out the day strong, we have in-person talks, keep you excited. So the first talk will begin with bypassing isolated execution on RISC V using side channel assisted fault injection and its countermeasures. And we have Shu Nashimoto here to give the talk. So I'll let you take it away.
Thank you for the introduction. I'm Shu Nashimoto from Mitsubishi Electric, Japan. Today, I'm going to talk about fault attacks on isolated execution on RISC V and its countermeasure. In the beginning, I'd like to show you the overview of my presentation. What I want to say in this presentation is, if critical instructions are skipped by fault injection, isolated execution on RISC V can be compromised. Our proposed attack skips the reconfiguration of the isolation settings at context switch and obtain the previous permission like this. We also propose a software-based countermeasure that makes the attack completely unsuccessful. Here is the outline of my presentation. It has 6 parts. Now, let's begin with the background. A trusted execution environment, or T, is a secure area of a processor isolated by hardware fault. It's a promising countermeasure to protect secure applications from malicious and vulnerable applications. So our attack target is T's. And ARM Trust Zone and IntelliGX are famous T-enabled technology. Fault injection attacks, inject malicious signals into a processor such as voltage, clock, and laser electromagnetic waves, and they cause instruction skips and data corruption. So they are a threat to security mechanisms and cryptographic operations. This table summarizes the feature of existing studies on fault injection attacks on T's. This table indicates that most of works target cryptography on IntelliGX and ARM Trust Zone. So we aim for a different way to attack another T technology. Here are our motivating questions. Is there any generic bypassing attack on RISC V-based Ts other than cryptanalysis? Is it a realistic attack, including fault parameter extraction? And is the bypassing attack on RISC V applicable to other T technologies? The answer is yes to all of them, according to our work. Let's take a closer look. First, I'll explain the security on RISC V. I'll present the major components comprising RISC V-based Ts. Ts aims to control access to ROM, RAM, and peripherals for each application or applications between secure and non-secure areas. For this purpose, memory access must be monitored. It is required to check memory access settings and decide whether it is allowed. A hardware unit called Physical Memory Protection, or PMP, handles this. And the privilege levels are vertical separation, which define the access right to security settings in ISO level. Let's see more details. The PMP aims to assign read, write, and execution permission to our specific memory ranges. PMP comprises of config and address registers, and they define permission and covered address respectively. A PMP entry or pair of PMP CFG and PMP error manages one memory range. And the PMP monitors all memory accesses and asserts an access fault exception in case of invalid memory access. And the privilege mode or vertical separation and define the access permission regarding memory access and exception handling. And RISC-V has 4 modes, namely U, S, H, and M modes. The significant point here is that only M mode can handle PMP registers. So M mode has the highest privilege and a U mode has lowest privilege, and U modes are controlled by all other modes. Next, I'll present our proposed attack. The goal of the attacker is to bypass the isolation and access the protected memory area by the PMP. Our basic idea is to inherit partial permission of the victim PMP settings by skipping the reconfiguration of the PMP. First, the attacker calls the victim application. At the time, the PMP changed along with the context. Next, the program flow returns to the attacker application, and the PMP register also restores. So attacker cannot access the up to the memory. So we use fault injection to skip the reconfiguration of the PMP settings. As a result, attacker can obtain the previous permission like this. But fault injection attack needs generally 4 information. That is target instruction and fault intensity and good injection timing and trigger signal. We mainly focus on first 3 information. Here is the attack scenario and attacker model. We refer to an trust zone use case that is like a smartphone's use case, where a user can use a blank area of a target device. According to the attack scenario, we construct the attacker model. Attackers can inject faults and run an arbitrary application in the lowest privilege on the target device and knows the T code, but it cannot be modified. Other applications are also unknown. Based on the attacker model, we propose an attack scheme, including the extraction of fault intensity and injection timing, based on using the profiling and target devices. This is because cross-device verification are more realistic according to attacker model and the attack scenario. And our proposed attack scheme has 5 steps. Let's see more details. I'll explain the most important aspect of the proposed attack, that is target instructions. And this feature makes our attack general and efficient. First of all, we have only 3 kinds of target instructions that rewrite the PMP settings. That is CSR write, clear, and set. This is because the PMP is one of the special registers and requires privileged instructions. So NET must use these instructions to construct T on RISC-V. So skipping the reconfiguration of the PMP setting is a common vulnerability for all RISC-V Ts. So our attack is general. Moreover, this feature makes it easy to extract injection timing and fault intensity. We adopted sidechain-based template matching and cross-device profiling for extraction of injection timing and fault intensity, respectively. And these are common techniques for all of us. And For normal force injection attack, extraction of these parameters takes a lot of effort, but we have few templates and few profiling instructions, so our approach is very efficient. Next, I show you the experimental results. We have two targets because we need to verify the generality of the proposed attack. The first one is the POC-T, or proof of concept T, which is our self-made T, and it has bare metal implementation. And second target is a Keystone, which is a very famous RISC V based keys, and it has Linux OS. So it's more complicated and more realistic. Let's see the first result. Our POC-T runs on the software processor on the FPGA board. We adopted clock fault injection with chip whisperer and EM leakage as a sidechain information. Our POC-T has 3 applications, and attacker tried to dump a secret key on up2. As I mentioned earlier, the attacker calls the victim application. Then, when returning to the attacker's application, they inject faults. First result is fault intensity. These results are obtained from profiling and target devices, respectively. And clock fault injection had 2 parameters, so these are 2-dimensional figures. And circled area mean the expected fault. So these results indicate that these 2 devices have similar trend. So cross-device profiling works. Next is the injection timing. The left figure shows an EM template from the profiling device and an EM trace from the target device. We applied SAD matching and succeeded to extract the execution timing. The red color means the true timing, and the black color means the identified timing. This indicates there are some false positives, but no false negatives. So our approach is effective and works. The last result is the exploitation result. We tried all combinations of candidates for fault intensity and injection timing, and finally succeeded to bypass the isolation and extract the secret key. I omit the details, but as for extraction for fault parameters, we need some margins for both parameters. Of course, regarding such margins, our approach is much more efficient than brute force. Next is Keystone. Keystone and its sample application land on the target device. And we modified the user code on the sample application. And we adapted EM5 with chip shelter. This experiment only verified the exploitation step. Here is the console output when attacking without and with EMFY. Without EMFY, the program halted with segmentation fault caused by load access fault exception. In contrast, with EMFY, such invalid access succeeded. So we confirmed that our proposed attack can be applied to more realistic keys. And I believe our proposed attack can be applied to any other RISC V based keys because it's general. The last topic is the countermeasure. Our goal of countermeasure is to ensure the PMP is configured correctly at each application runtime like this. To insert the PMP verification process is a naive idea, but it's meaningless. because such verification process can be skipped by the for the injection. So we aimed for an approach where the program flow transits to a abnormal state if the PMP reconfiguration is skipped. But how to do that? Based on the approach, we proposed jump address masking, and it has two phases. First, it masks the jump address with the hash value, hashed PMP values at build phase, and unmasks the masked address value at execution phase. If the PMP configuration or unmasking process is skipped, the program flow transits to our broken address, and which causes an access fault exception. So we correctly integrated the verification process and the program flow. But we note that a hash function should be carefully selected so that the broken address doesn't point to the buried address. And we, I omit the details, but we prove that our countermeasure has complete resistance to possible attacks. Now let me summarize my talk. We proposed bypassing attack against RISC V based Ts. It skips the reconfiguration of the PMP settings by force injection, and it's general and efficient. I don't make the details, but in terms of trust zone, our attack can be applied to application isolation, but not to world isolation. And our experimental results showed that our attack is feasible and general, using the experiment using two kind of T implementation. And we also propose the jump address masking, and which prevent our attack completely. And future work includes implementation and demonstration of the proposed countermeasure and application of the proposed attack to trust zone-based Ts. And here is some additional information. We made our POC-T open source now, so you can access our POC-T from the RISC V Exchange website. That's all of my presentation. Thank you for your kind attention.
All right, thank you very much. So we'll start with questions in the room. No questions yet. So I did look before too, and the code was on GitHub. This was true. If you were seeing people do work extending your code, what would be the most interesting thing someone could work on? You had some future things there, but I was curious what you would like, to see as a next step with this.
Next step for what?
So using the available code you put on GitHub for the T, so that's available for people to work on. I was just curious if you had advice to someone that goes and downloads it and wants to implement something.
So your question is, how can we use our POC-T?
Yeah, or what should people do with it? What would you like to? What would you like to see them do with the project? If you
POC-T, about POC-T?
Yeah, but the proof of concept T.
Okay.
You must have something that you said, I want you to do this. I wish we had time to do this.
Okay, thank you. Yes, and so what is the question?
So what would you like to see them do with?
Okay.
Implement different types of attacks or different protection mechanisms, or what do you think?
Thank you for the question. Okay. I understand. So I talked about our POC-T 3 days ago, but I think there are many usages for our POC-T. For example, to construct advanced T that has physical protection and evaluate its security and the performance, such as I think control flow integrity extension for RISC-V is an interesting feature. And I believe such mechanism has partial resistance to force injection attack. So such usage is very interesting, I think.
Cool. Thank you very much. Now, were there questions in the room? I don't see it online. So I think we'll thank you again with that. And move on to the next.
If your name is Namhoon Ko, sorry for the pronunciation, and you are from Korea, I have your passport. It's going to be at the registration desk. If you are this person or if you know this person, please send the person to the registration desk. Anyone? Is he here? Namhoon Ko, Korea? Otherwise, we have to auction it later.
I mean, they're still in the country, right? So this is. So we have the honor of Tim Fritzman will be giving us the next talk in the session. And I think there's 7 co-authors, so you're still within the allowable length of co-authors here. This is acceptable. So this talk on masked accelerators and instruction set extensions for post-quantum cryptography given via Tim. So take it away, please.
Yeah, thank you.
So yes, I will present it for mass accelerators and
Okay, so again, I will present the talk masked accelerators and instruction set extensions for post-quantum cryptography. This was a joint work with Michel Debabria, Patrick, Thomas, Ingrid, and Georg. First of all, in the presentation, I will quickly give an overview and a motivation. Then we will have a look at some masking methods in order to protect the post-quantum cryptographic schemes Saber and Kyber against side-channel attacks. Then I will present some masking accelerators to boost the performance of a hardened design. And finally, I will provide some system integration and experimental results. So several works already analyzed countermeasures to protect post-quantum cryptography against side-channel attacks. Nevertheless, a clear picture regarding the implementation costs for these countermeasures is still missing. To deepen the cost analysis in this work, we focused on masking as a provable countermeasure against differential power analysis. More specifically, we presented a masked hardware software co-design for the PQC finalists Kyber and Saber. We developed a generic number theoretic transfer multiplier, which is suitable for most lattice-based scheme. And we developed a novel masked ciphertext compression technique and also masked accelerators for critical nonlinear operations. So a public key encryption scheme can be divided into the following operations: key generation, encapsulation, and decapsulation. Whereas the decapsulation is the most critical part, as it uses the long-term secret key in order to decrypt the ciphertext. Now, masking randomly splits the secret variables, such as the long-term secret key S, into multiple shares in order to break the correlation between the power consumption and the currently processed data. But masking Saber and Kyber is quite different, and this is especially as Kyber is based on the module learning with error problem, while Saber is based on the module learning with rounding problem. And also Kyber uses a prime modulus and Saber a power of 2 modulus. So here we have some small differences, but they have a larger impact in the implementation costs. But now let us have a look at the masked decapsulation operation of Saber. We have as input our ciphertext pair C1 and C2. Then we will perform some operations, in particular with the long-term secret key S in order to decrypt. And the decapsulation has also a re-encryption step in order to obtain the ciphertext pairs C1 prime and C2 prime. Now, when we have computed the re-encryption, we can check if the input ciphertext and the output ciphertext is identical. And if it is identical, we can forward the decrypted value to the output. So this re-encryption will prevent chosen ciphertext attacks. And now we do not compute all our computations in a plain variant. So we duplicate the operations and we make it in a masked way. So for example, we split the input, the ciphertext C1 into 2 shares, but also the secret key into 2 shares. And now we have different operations in our masked decapsulation. In yellow, we have the linear polynomial multiplication, which is usually very costly. And then in blue, we have several nonlinear operations, for example, the hash function G, extendable output function, binomial sampling, A to B conversion, B to A conversion, and masked ciphertext comparison. Now, when we look at Kyber, the figure looks a little different. The main differences are that Kyber uses 3 sampling instances instead of only 1. And this is due to the learning with error setting, where we have to sample also error terms. And with learning with rounding setting, we do not have to sample them, as the error terms are implicitly generated by the rounding effect. Moreover, Kyber has a little bit more complex B to A conversion and also a more complex ciphertext compression. Now let us have a look at the individual components. First at the linear operations, as already said, they are duplicated in the masked setting, but that means also that the execution time doubles. Therefore, it's extremely important to have a very fast multiplication, and in particular, a fast polynomial multiplication. Usually, the multiplication is done with the number theoretic transform. While it is very efficient, it is not always directly applicable for all the schemes. For example, Sabre and Andrew do not specifically design the parameters for the entity. However, we can lift the prime to a higher so-called entity-friendly prime. Then we compute the polynomial multiplication and apply the entity. And after the computations, we can switch back to our original prime. Therefore, we developed in our work a generic entity-based ring arithmetic accelerator, which also supports the so-called prime lift and also supports non-entity-based schemes such as Sabre or Andrew. The final architecture is shown as in the slide. The main computing element is the modular arithmetic unit in the lower corner. And yeah, so this unit supports all the entity operations. It supports pointwise operations such as additions, subtractions, and multiplications, positive and negative wrapped convolutions, and also it supports the early entity abort, which is specially used in Kyber. So we use the 4 address units in order to perform these operations, and to control the circuit, we have several input signals. Now let us have a look at the next components. While the ring arithmetic requires an arithmetic sharing, the nonlinear operations shown in the gray boxes require a Boolean sharing, and therefore we require some efficient methods to switch between arithmetic sharing and Boolean sharing. So the arithmetic sharing splits the secret variable x into 2 edited parts, while the Boolean sharing uses the XOR operation. And the goal of the conversion is now to efficiently switch between these 2 sharing types. So previous works already developed some generic conversion methods, and one was proposed by Corona and others in 2014, which is based on the secure addition. This one is very efficient for hardware implementations, as the secure adder is well suited in hardware. And is also well suited for power of 2 modules and also for prime modules. So one method which is based on the B2A conversion, so on the A to B conversion, on the arithmetic to Boolean conversion, is the masked ciphertext compression. The masked ciphertext compression reduces the key sizes of the ciphertext, and it can be computed according to Formula 2. While the compression, or the most difficult part in this equation, is the division by the modulus Q. And yeah, while this is easier in a non-masked setting, this is quite challenging in a masked setting. And previous works therefore proposed an interval comparison instead of using the division. But this is not possible if we have higher compression parameters D. So we cannot split easily into many intervals and then make the comparison. Therefore, we have developed an alternative approach, which in fact uses the division. But now let us have a closer look at the division. If we illustrate X prime into two shares, we can obtain the following figure. And the division has in principle infinitively many decimal places. And this makes the carry computation extremely difficult if we have two shares, because we do not know what the carry of the combined shares is. However, in our work, we found out that in principle, F decimal places are sufficient in order to compute a correct carry computation with two shares. So the masked ciphertext compression tolerates an approximated quotient. And the amount of decimal places F that we require is dependent on the scheme and on the modulus. For Kyber, it is, for example, 13. Now let us have a look at the circuit that is used for the ciphertext compression. So for the multiplication by 2 to the power of D, we shift the input or the input shares by D positions. And then in order to avoid floating point arithmetic, we shift again by F positions. So we shift in total by D plus F positions. Then we will perform the multiplications with the inverse of Q. We will have some correction term in order to avoid the rounding operation and instead use the shifting operation. And before we shift back to our original or to our desired result, we apply an A to B conversion, and we apply this A to B conversion in order to avoid the complex carry computation for the shift operation. So the shift operation in the arithmetic sharing requires a carry handling, but in a Boolean sharing, we can neglect the carry operation. So as you can see, we have quite simple operations and only one A to B conversion in order to handle the masked ciphertext compression. Now the binomial sampling is also quite critical as it needs to combine multiple shares in order to compute the operations. The centered binomial distribution is an approximation of the Gaussian distribution and is frequently used in lattice-based cryptography. It can be computed according to equation 3, which basically accumulates the subtraction, the bitwise subtractions of two independent integers, x and x prime. And this subtraction or this accumulation, this bitwise accumulation can be computed with the following adder tree, which contains the half adders. First, we input our bits of the variable x, and then after we have computed the sums, we input the negative input of x prime, and at the end we have the summation. So this is quite simple in a plain design, but how does this look in a masked setting? So one approach is to use the threshold implementation principles, which is a function-based approach based mainly on the incompleteness property. And then we divide our addition or our half adder in two separate functions for the sum and for the carry computation. And if we apply then the threshold implementation principles, we obtain the equations 4 to 7. And we can see that the linear operations, the XOR operations are quite easy to compute. We can simply share-wise compute them. The nonlinear AND operation is a little bit more tricky. In order to have a first order secure implementation, in total we require 3 shares. But we can see that, for example, in equation 5, always 1 share is missing. For example, equation 5, the share 0 is missing. Equation 6, the equation 1 is missing during the computations. And in equation 7, the share 2 is missing. Now, when we turn the previous adder tree with, when we turn this into a threshold implementation, we can see that the circuit is already quite complex. And as you can imagine, this has quite high resource consumption and also randomness requirement. Therefore, we looked for an alternative approach based on the domain-oriented masking principles. And here, instead of 3 shares, we require only 2 shares in order to get in first order secure implementation. And as you all can also see in the slide, the circuit is not that complex, so we have much less components here. The principles of the DOM AND that we have used for our carry computation is to split the secret variables into separate domains, and all the computations are performed within the domain. And only for the domain crossing operations, we use fresh randomness, in our case, the R value. So as you can see, the circuit size really reduced, and in total, we have 40% less FPGA slices here, for example. Now, all the different accelerators that I presented and also some more were integrated into a 32-bit RISC V processor. And this includes, for example, a Ketchak accelerator. And also for the nonlinear Ketchak part, we have developed a G accelerator. Our binomial sampling adder tree based on domain-oriented masking, and a secure adder for A to B and B to A conversions. For our ring arithmetic accelerator, this one we placed outside of the processor core, as we want to strictly split the 32-bit operations of the RISC V core and the higher data path of the ring arithmetic accelerator. So when looking at the performance results and cycle counts, we observed that our masked implementation has an overhead of factor 4.5 for Kyber and a factor of 2.6 for Saber. So it turns out that Saber is a little bit easier, or let's say easier, maybe cheaper to mask. And this is mainly, as I said, due to the module learning with rounding instead of the module learning with error, and also the simpler power of 2 moduli. And so in summary, we developed hardware software co-design for Saber and Kyber. We developed a generic masked ring arithmetic accelerator and also accelerators for the critical nonlinear operations. So this summarizes my talk. Thank you very much for your attention.
Thank you very much. There we go. So questions in the room? See any? One question I had on, actually 2, but the ARM, the results for the software implementation, you also showed ARM and RISC V. Was there any difference, I guess, between ARM and RISC V itself that impacted, say, the cycle count if you implement the same algorithm, or you'd expect those to be similar, or how would that?
In comparison, we achieved a lower cycle count, but this is mainly as we have a lot of hardware accelerators also. And yeah, so yeah, you can see here in comparison, for example, yeah, for the master implementation, yeah, we have one.
Yeah, so I guess the question was that it's mostly related to your work and not like if you took your code, compiled it on ARM, I'm assuming the cycle count would be a similar number, or is there any implication on the RISC V instruction set out of interest?
So yeah, for example, the ARM Cortex M4 has many nice features, and yeah, for example, the vectorized arithmetic is quite nice that we do not directly have in our RISC V platform here, but we can also write some instruction set extensions.
Makes sense. Were there questions in the room? Let's see. I don't see any questions online, so I think with that, we'll move on to the next speaker to keep it on track. Thank you very much again, Tim. Then click once. Great. So for the final talk to close out Ches, we'll have an interesting work on composite enclaves towards disaggregated trust execution, and Moritz Schneider here will take it away. Thank you very much.
Thanks. So yeah, welcome to my talk. My goal is very easy today. I try to keep you from falling asleep. This is the great honor to give the last talk, or curse, depending on who you ask. Today I'm going to use mostly pictures, no formula, no nothing, you know, try to keep it light for the end of Ches. Good. So first I'm going to talk a bit about modern computing and sort of our view on this. And this is mainly from sort of supercomputing space as well. In the past, we had processors, we had memory, and we did all of our computation using these two things. Nowadays, we have many devices, you know, from personal computing devices, keyboards, you know, other input devices, cameras, microphones, to accelerators, you know, network cards, graphics cards, accelerators, and all of this is basically used predominantly now in modern computing because we need more performance. Now, the main thing that's okay, one more example. You don't have to trust me with this. This is a recent ARM, I think it's an Apple processor. And here you see, like, from the floor diagram, only a small amount of the floor of the area is spent actually on cores, on compute cores. Most of it is spent on neural processing engines, on GPUs, and so on. Now, if you look at another area, which is trusted computing, here, you know, something a bit weird happens because, like we heard before from a different talk, these are all trusted computing proposals from industry and academia, but all of these are based on one processor, on the main processor. Now, right, modern computing goes to accelerators, trusted computing goes to a processor. There's already some disconnect here. Bad timing, I know, but NVIDIA came, like after we wrote this paper, NVIDIA came with their proposal, so it's kind of a, but I'm going to talk more about this later. But for now, let's just ignore it, and yeah, we continue on. So the main thing that's also maybe you should take away, or if you want to take away something, take away this thing, that, you know, modern computing, we go towards custom devices, we go towards acceleration, specialized devices. But in trusted computing, we just say, well, okay, let's go back to the CPU. And we believe that this is sort of an inherent, you know, flaw of the current designs. And yeah, would be nice to sort of fix this. Now, it's, as I said before, it's not just computing. We also have input devices, right? We have sensors, and we have cameras, you have GPS devices. You could think of, you know, I might want secure location I might want a secure video feed. I might want, all of these things. I have light sensors that I want to see if the light is on or off. Actually, this entire thing is not, trusted computing doesn't support any of this, mostly. There are academic proposals for individual things, but mostly it doesn't support any of these things. Now, one thing we did actually, to go back here, one thing that we sort of did to build all of our stuff is that we said, okay, let's assume we have trust execution environments. So we heard in the talk before what these are sort of. So let's assume we have these systems on all of our devices. So we have one on the processor and we have one on the GPU, the network card, and so on, all sensors and so on. Now, this is not new. People have been doing this in academia. There's been people that did this on GPUs, people that did this with FPGAs, and many more. And now also NVIDIA doing this on actual commercial devices that you can, I'm not sure if you can buy it right now, but they announced it like a year ago or something. Now, one thing that you have to think of if you build a system like this is the original attacker model for many of these trusted computing proposals are very strong. So for example, SGX is one of the most prominent ones. We have local physical adversaries. We have entire software stack is considered malicious. And yeah, the main issue that is there with this attacker model, like we would like to have this, right? But if you look at, for example, sensors, I mean, a local physical adversary is a bit useless, right? Because I mean, I can just take a flashlight, point it at my sensor, and it's going to read something else, right? So essentially, the local physical adversary sort of falls out the window if you consider sensors, any sort of input-output stuff. For accelerators now, there's an asterisk, right? If you only consider computing, you can probably do it with the local physical adversary. But yeah, in general, if you just want to support everything, you probably have to exclude the local physical adversary. So maybe a quick recap for some of you that don't know how this works. Essentially, how do you interact with peripherals on current systems? It's pretty easy. Here you have memory. This is a physical address space. And essentially, after some address, you have DRAM that's all mapped there, so you can access this based on addresses. But you also have other devices in memory ranges, or sorry, address ranges that are not part of memory. So you have UART, you can have PCI devices, stuff like this, and you communicate with these using, we call them memory mapped I/O, memory mapped registers, and you can just access an address like this, and they will respond or they will interact somehow with you. Then there's the second way of interaction with specialized hardware, and that's DMA, right? We have direct shared memory. And these devices are usually more geared towards higher speeds, accelerators, and so on. But these are sort of, the main thing is these are the two options that you have nowadays to communicate with peripherals on normal application processors. Now, I'm going to tell you, this is cool because we have addresses and you can use memory isolation mechanisms. Let's hope this fault injection attack we heard before doesn't work for now. But yeah, I'm going to tell you PMPs are great. Don't disregard all of the fault injection attacks. Good. So now, to simplify this a lot, what we want, we have these, we call them enclaves in this space. These enclaves are sort of isolated containers. They run some codes that is sort of you can attest to remotely, and then this code does some computation. Traditionally, this only did it on the processor, on the main processor. And now what we want to do is we want to also enable these containers to talk to peripherals, right? Let's say you want to talk through memory mapped I/O to a keyboard, or you want to talk through DMA with a graphics card. Or actually, you might want to have a combination of all of this, right? You might want to have a trusted container that records video and then passes this through some computer vision pipeline on the graphics card. And all of this sort of, some of these individual parts you can do with current approaches, like NVIDIA's approach, for example, you can essentially build a container that is shared that can work with the GPU itself. So you can have sort of a thing that works on the main processor and the graphics card, but you cannot integrate any other stuff. For example, a camera. Now, one of the main problems that there are with these things, sort of to simplify it also a lot, is that the attacker basically wants to replace a device at runtime. You basically you plug it out, you plug a new device in, and that's how you do it, right? So what we do to simplify it a lot again, we essentially facilitate all of these connect and disconnect routines by doing explicit things in trusted code. So essentially, if you want to share memory, or if you want to sort of share memory between a container and a peripheral, you have to do this explicitly through a call to some trusted code. Now, if one of those two dies, let's say that GPU is blocked out, then what's going to happen is that this piece of shared memory will just it's no longer shared, right? It's only accessible from the software on the processor, and you will need to explicitly disconnect it before any new device or any new entity gets access to it. It's now very simplified a lot, but if you have more questions, you can come talk to me later. So all of this we base it on Keystone, as the other talk before did as well. Very cool open source TE environment. And we used open source RISC V cores as well. We had to extend some of the cores, but all of this is now open source, so you can access it if you want. On the left, you see an FPGA that's running a 64-bit RISC V core. That's, I think, from I think it's called Ariane, but now it's called CVA6. Not sure if you know, but you can find it online. And on the right, you see sort of a simulated peripheral, right? Because we had to have a peripheral that's supposed to have some sort of capabilities, some sort of TE capabilities. And here, I think it was a 7-segment display, and the Arduino we use for software running on the peripheral itself. Obviously, this is only output, right? Very simple example. So what we did to do this, actually, first I forgot. First, we also measured sort of what our approach does in terms of overhead, because we have to have some extra checks in context switching, and context switching is very important in software development. And so what we did, we measured context switch based on how much memory we share, and essentially the context switch itself, which is the light green line here, it doesn't increase that much. It's basically the same. However, to create a new container, a new enclave, you have to do a lot of checks, and you have to do the main overhead is here, the virtual to physical translation, parsing and stuff. So this is sort of linear with the size of the shared memory size. Now, I showed you before the very simple sort of device. You have a 7-segment display they want to connect. Now, what we also wanted to look at is how we can connect to a large compute style device. So what we did is we took this is a very simplified view of a big graphics card. We have DRAM, we have a lot of small compute clusters, and we have a few bigger cores that facilitate data movement and stuff like this. And what we did is we took one of these sort of small boxes here. This is the compute capability. And essentially, each of these small boxes, we sort of model them as, there are a few small cores that do some computation, and they have local memory and so on, and then they're sort of connected. And all of this is also a RISC V based accelerator that we took, and then we extended it to add some PMP capabilities to this. We did some optimization so that we don't have to have PMPs on every single core, like full-fledged PMPs. So we essentially said we're going to leave the configuration of it to only one core, and then mirror the configuration through all of these through one of these sort of clusters, right, that we have. And this is relatively small. So we did synthesize this in 22 nanometer technology, and it's okay. So the one thing that I have to say here, and that's why the asterisk is there with the 4, is that essentially we had to adapt the speed. So essentially we wanted to, for these 2 points they wanted to evaluate, we wanted to have sort of an optimal AT plot point that we selected. So we wanted to have sort of wanted to select the sweet spot of the design so that the comparison makes sense, because otherwise, one just blows up or nothing happens. So the 4 actually runs a bit slower. So if you add this isolation technique we added, you lose like 10% performance, but area-wise, it's sort of the same. So that's also what happens here is essentially we lose performance. So we add overhead in the cores, but the floating point unit essentially gets smaller because we lower the speed. That's why sort of the offset comes in. So one thing also I want to talk about is limitations, right? This is we did sort of very simple prototyping of these things. But you essentially have a problem, especially if you go to real systems, you have to write drivers. And drivers are large, and we don't want to trust large drivers. This is an inherent limitation with all of this. This will be a limitation in the future as well for trusted computing on devices. This is also a limitation of NVIDIA, how their new approach works. So, you know, if any of you has a smart idea, please come talk to me. And the other thing is sort of remote attacker. Since we can no longer tolerate a local physical attacker, it's kind of bad. We lose a lot of the security guarantees that you got beforehand. The one thing I can say about this is for compute only, you can still tolerate local physical attackers. The thing you have to do there is you have to do some bus encryption, you have to do some key exchanges on, before doing all of this. This is also quite hard to do, to evaluate, academically, because all of these things are essentially behind large paywalls, and you don't get access to any of these systems, especially want to encrypt very high speed buses. So it's going to be hard to evaluate in the future, but would be fun. And then lastly, thanks to all of these awesome open source projects that made these things possible. Like without this, we couldn't do any of these things, and hopefully in the future there will be more. And yeah, with that, I'm done with my talk, and thank you all for listening, and I hope you had a nice chess.
All right, thank you very much. Because you said you ignore fault attacks, I had to switch my shirt with little lightning bolts, so you can never forget fault attacks. All right, so first questions in the room. And if not, I wondered if, all right, I missed one. Okay. You could comment on, actually the first talk talking about countermeasures to fault attacks, and if that would be easily applicable to your sort of PMP solution, or is this different, or just at a high level?
I'm pretty sure they would be applicable. Like all of the defenses that you can do, masking, fault injection, mitigations, all of this is what we did essentially is mostly on the software level, right? So essentially all the defenses you can imagine, you can apply that work on other circuits, I think.
Very cool. So look at that great synergy within the session already here, open source. Okay, so we'll see if there's other questions in the room. And I check online. Okay. So with that, I think we can thank you again for this great talk. And yeah, so thanks again to all the speakers. It was a very great session. And I think now we see Benedict for one last time. Nice to see you. Now we wait for 5 minutes to let the other folks from the second aula come over here so that we do the closing final remarks all together in this space. So just hang on 5 minutes.
All right. So we have been informed that whoever wants to be in this room is in this room. So we don't have to wait any longer. It went pretty quick, as always. 4 days of chess are over. This is the last session, the closing remarks. And so we have to say you actually really did it again. What happened yesterday? It was crazy. This morning we had an email from this band, from this glorious band. This is what they wrote to us. So they enjoyed it absolutely. And so we should thank you from them. They had a great night as well. So we forward this message. I was going to put a couple of photos on this slide. Then I said, no, what happens in Leuven stays in Leuven, all right? So we are going, with all the photos that we're taking throughout the conference, we're going to make a selection of those available on a photo wall later. You will get an email with a link. Maybe not so many photos from yesterday evening from people dancing, because what happens in Leuven stays in Leuven. But so these photos will be made available. Many people asked already, so don't worry about that. That will come.
Yeah, we tried, when we started organizing this, we said we have to do something special about this chess. And I think we did something special, something that you would remember. It was the first after pandemic chess, and we had to make you remember it somehow. And we hope 10 years later, you're back again. This is becoming a tradition. Every 10 years in Leuven. The young generation is ready for you. A bit of statistics, we like statistics. So we had today the last registrations, of course, for online registrations. We had 520 in-person registrations in the system, 177 online from 39 countries. This is the chart with all the countries. Of course, we cannot see all of them, but the first numbers you can see on the left side. Germany is the winner again. Belgium follows up, but we couldn't beat them. And of course, nothing surprised. Just the day before the early bird, everybody starts to register, and the pick is then. Please, next time, try to be a bit more organized and register on time so that we know how much pullovers to order, how much chocolates to order, and things like that. Would be useful. I would like to thank our sponsors, but before I thank our sponsors, I would like to thank all these amazing young people that, thanks to them, please come to stage. Everybody, please. This is the future of chess, as you can imagine. And we couldn't have done it without them. Thank you very much, guys. Of course, we needed also lots of sponsors. And as I said, we are very grateful and we really appreciate their support. And next stop for chess will be in Prague. And here we have the next general chair to tell us more about this.
Okay, good afternoon. My name is Martin Novotný. Hanna Kubatova and I are general chairs of the next chess in Prague. So it will be by the beginning of September. So the weather is still better. Usually it's very good in that time in Prague. If you have not been to Prague, you should come to Prague to see how Prague is a beautiful city. We also have very good beer. And by the way, the building, the venue where we are is the building where Pluto was excluded from the list of planets in 2006. So you will see the building. And maybe I think that you deserve explanation why there are 2 chess conferences in a row in Europe. As you know, the last physical chess was in Atlanta in 2019. And chess rotates, so it is in Europe, then in America, and then in Asia. So chess for 2020 was planned for Beijing. Due to the COVID situation, it was shifted twice. And so this year's chess was planned to be in Beijing. Unfortunately, if you have looked at the news, you know that the COVID situation in Beijing unfortunately started to develop again after the beginning of the year. And for this reason, Svetla and Benedict and all their team decided to make chess for us here. And they did it so well, even if in the short period of time, only just six months, that we would have really hard problems to beat them the next year in Prague. So, and I think that they all deserve one huge applause from all of us again.
That's it. That was it, Chess 2022. Have a safe trip back home, and hope to see you again next year. You keep it or I take it? Okay.